Hello again, Physics 20s, and welcome to the last unit of study in Physics 20 on mechanical waves. And before I do get going with this lesson, I just wanted to point out that I'm going to be going back and forth between the lecture notes and an animation of a couple different types of mechanical waves. And if you're interested in checking out those wave animations at the end of the lecture, you can see the website link on this slide. Learning outcomes are to describe mechanical waves as particles of a medium that are moving in simple harmonic motion. 2, compare and contrast energy transport by matter and by waves. And 3, define longitudinal and transverse waves in terms of the direction of motion of the medium particles in relation to the direction of propagation of the wave. And 4, define the terms wavelength, period, frequency, and amplitude as they apply to describing transverse and longitudinal waves. So we're going to get things going by providing a very, very general definition of what a wave is. A wave is simply a carrier of energy, but it's all about how a wave actually carries energy. And the way that a wave moves energy across a certain distance is the result of individual particle vibrations. So let's take a look at a substance that's made up of a bunch of particles and examine these individual particle vibrations. So I'm going to go to that animation for the first time here. Okay, so let's look at this one where it says transverse wave. And don't worry, we're going to define a transverse wave in a moment. And what I want you to do is just focus on an individual particle in this medium. So this medium that we see right here, and when I say a medium is a region that has like a constant density to it. So one medium could be water at a very specific temperature. Another medium could be air. Another medium could be solid material that makes up the ground. So let's pretend that we're looking at a side view perspective of a water wave. If you focus on one individual particle, okay, one individual particle just appears to be going just straight up and straight down, just vibrating, oscillating up and down, up and down, up and down. Now, if you envision for a moment that if I put an object on top of this wave here, like maybe like a flutterboard or a rubber ducky, it would seem like the wave would cause the object to kind of like move towards the right. It would go from the left to the right-hand side. So the direction that your flutterboard or your rubber ducky would go, that'd be like the direction that energy is being carried or transferred. But the neat thing about a wave is it's doing this energy transfer as a result of just particles that are just oscillating over a very, very small distance. Okay, let's go back to the PowerPoint slide now. All right. We're going to take waves and break them into two categories. So for Physics 20, we're interested in mechanical waves. Mechanical waves require a medium, which is a specific material, usually with like a constant density to travel through. And again, examples of a medium could be air, it could be water, it could be the ground. An example of this is sound. Sound is a mechanical wave, and despite how cool movies like Star Wars and TV shows like Star Trek are, where you can hear like gigantic explosions in space, probably not realistic, because the way that sound works is, for example, if like, let's grab a pen here. This is kind of like a very basic explanation. So let's say I just clap my hands, like a really big clap sound. That's supposed to be like the bang from like the clap. Okay, now what happens when you clap is that any particles that are close by would have some energy transferred to them. And what would happen is we transfer energy to these particles and it would cause them to vibrate side to side. This guy would collide with this next one. Then this guy would start vibrating. It would collide at the next one, cause this one to vibrate, collide at this one. And eventually this would reach your eardrum, and then something involving biology, which we don't talk about in my physics classroom, would occur where you can actually interpret the sound. But if you don't have the particles in the air, then there's no way that you can actually transfer the sound energy from one spot to another. Our second category of waves is an electromagnetic wave. This is something we're only going to talk about in Physics 30, although I'll provide a very, very just quick definition of it right now. An electromagnetic wave does not require a medium to travel through. When I say no medium is required, it means that there's no particles in whatever area you're looking at, or you don't need a material to travel for it to travel through. That means that an electromagnetic wave can actually travel through empty space. So the best example of this would be all forms of light. Visible light, ultraviolet radiation, they can definitely transfer from the sun to the earth here. This is an illustration of an electromagnetic wave, which shows that you have perpendicular and oscillating magnetic and electric fields. But since we have no idea what an electric or a magnetic field is yet, we're not going to talk about this yet. Again, in Physics 30, we'll start talking about electricity and magnetism, and then eventually we'll start to define what an electromagnetic wave is. But for the time being, we're going to focus just on mechanical waves. We can actually take mechanical waves and we can break them into two subcategories or two classes, starting with a transverse mechanical wave. A transverse wave is a wave where the particles in your medium vibrate perpendicular to the direction of motion of the wave energy. Okay, so let's go back to the animation again. So this one we first look at is an example of a transverse wave. If you look at an individual particle in this medium, and an individual particle in that medium is just moving up and down, up and down, up and down. So that's the direction of the particle vibration. The direction the wave energy is being transferred, and we can refer to that as the direction of wave propagation. So the direction of wave propagation would be the direction that your energy is being transferred. Again, I said you can envision it as if like you put like an object on top of this, like a flutter board, and just identify what direction is it going. And it seems like it'd be waving towards the right. So let's go back to the PowerPoint and let's try to define this a little bit. Okay, so let's pull up the pen here. Okay, so in that medium, here's my particle, and my particle was vibrating in a direction that was up and down. The direction of energy transfer was propagating towards the right. So the angle between the direction of the particle vibration, the direction the wave energy is being transferred, that is a 90-degree angle. And if you have a 90-degree angle between those two things, between the direction the particles in the wave vibrate compared to the direction the energy is being transferred, that's what we define as a transverse wave. Now, transverse waves are the kind of waves that probably when I say to you, like, envision what a wave looks like, you would probably come up with this shape that we've already seen back in the simple harmonic motion unit. Okay, it's got that wavy type shape to it. What we're going to do is we're just going to look at this and we're going to define a bunch of different quantities on it. We've already talked about a bunch of these quantities from the simple harmonic motion unit, because we define different properties of this wave type shape. We're going to go over it again. Yeah, I've already made note of this. We more commonly refer to the direction the wave energy is being transferred as a direction that the wave is propagating. So the amplitude would represent your maximum displacement from the equilibrium position. So what's going to happen is, so let's pull up a little particle here. Let's do it in green. Okay, so equilibrium position would be the spot where your particle will be at rest. Okay, so if it's not at rest, it's going to oscillate all the way up here. It's going to oscillate to the up position and then to the down position. So it's going to go up, down, up, down, up, down. So from the equilibrium position, which is where this particle would be at rest, the amplitude is your maximum distance from that equilibrium position, and we'll call that A. The highest spot that your particle vibrates, so again, your particle is going to vibrate up all the way up here and then back down. The very uppermost portion of the wave is what we call the crest. And then when the particle then vibrates, so that's at the lowest position, we refer to that as being a trough. The way I remember this is I think if you're like brushing your teeth with Crest toothpaste, then your teeth look great. So you're on the top of the world. You're at the highest point. And on the other hand, if you're drinking out of a horse trough, you'd probably be at a very, very low point in your life. Wavelength. Wavelength is the horizontal distance between two crests or troughs. Okay, first of all, the symbol we use to represent wavelength is the Greek letter that is lambda. I think that's how you spell it. The way I like to draw the lambda symbols, I kind of drew like a curved slide and just put like a support at like a little bit of an angle. That should have been a straight line, but drawing with the drawing tablet is weird. By the way, I'm using a different drawing tablet. If you're wondering why my writing looks so robotic, this drawing tablet doesn't seem to like to draw curves very easily. Okay, who cares about that though? Okay, so your wavelength, easiest way to identify it would be you start at one crest right here, and then you can go over to another crest. That horizontal distance from crest to crest is your wavelength. Or it could be the horizontal distance from one trough to another one. Or the other way to think about it is it's kind of like when you've passed through one wavelength, the wave then starts to repeat. So if I look at this here, if I started at the very top and I followed through the actual shape of the wave and I asked myself, when does the wave start to repeat again? Okay, so it dips down and it comes back up. And at this point right here, it's about to start dipping down again like it did at the beginning over here. So that's where it begins to repeat. So that's all your wavelength is. It'd be the horizontal distance, I suppose, before the wave starts to repeat itself. The period is the time it takes to travel one wavelength of distance. I like to think about this a little bit differently. If you're wondering like what one period is, and we can relate this to simple harmonic motion. So what your particles are doing is your particles are always, they're vibrating up, they vibrate down. So they're always going to an amplitude and then passing through the equilibrium position. So this is an example of simple harmonic motion. There's some kind of seemingly restoring force that's making my particle go back towards the equilibrium. The one way I would think about what the period is, if you took a particle here, and what happens is when the problem with this picture is it's a static picture. It doesn't show the waves actually oscillating, but what would happen is the time it would take a particle at the crest to vibrate down and then come all the way back up, that's supposed to be a down arrow and an up arrow. That would be your period, okay? So the period would be the time it takes a particle in the medium to basically, if it was at the crest, to go down and then come back up. This would be identical to the amount of time it would take your wave energy to cross a wavelength of distance. So they're the exact same things. There's two ways you can define it. Time it takes like your energy to propagate over a wavelength of distance, which would be equivalent to the time it takes a particle in the medium to basically go down and come back up. So it returns whatever position that we were looking at to begin with. Frequency, and again, we know it as that inverse relationship between period, is the number of wavelengths that occur in 1 second. So again, there's a couple of ways you could define this in terms of the frequency. So one way is if we looked at this, and if we measured how many times does this particle go down and then back up, down and then back up in 1 second, that would represent the frequency, okay? So the number of oscillations per second. The other way we could look at it would be in 1 second, if you want to look at the wave energy, how far would the wave energy propagate in 1 second? That would also be equivalent to the frequency. So just two ways of looking at how to define the frequency of a wave. One is from the perspective of the horizontal distance that the wave energy is propagating, and the other is based on the oscillating motion of the particle. Oh, here's a picture of me in a rubber dinghy, which is like my favorite pastime in the summer, where I just sit in a rubber dinghy and I just observe wavelengths, crests, and troughs. So on this particular day, I'm sitting in the rubber dinghy and I'm looking at it. And if you can look at the illustration, a crest, so you can see these little ripples, these circular ripples that are actually forming around the source of the wave. A crest would be like the uppermost portion of the wave, and then a trough would be where it dips down. The equilibrium position would be like where the water's at rest. Maybe like somewhere over here, we can kind of see the water more at rest. If you're wondering like what the level would look like. And the wavelength would be, you could go from one crest, which is right here, over to another crest. Or if you wanted to look at the troughs, you could also go from a trough to a trough. So for example, this could be going from, oh, I can't see that. Let's do green. Okay, going from here to there. That would also be my wavelength. And by the way, if you haven't figured it out already, that is not actually me in the rubber dinghy. This is just a picture I got from the image bank of the textbook that I never use. Second class of a mechanical wave is a longitudinal wave. Longitudinal waves are ones where the particles in the medium vibrate in a direction that is parallel or in line to the direction that the wave propagates or the energy moves. Okay, so once again, let's go back to the animation. Okay, so this guy up here would be an example of a longitudinal wave. Now, once again, if you just trace what one particle is doing, I think it might be easiest to look at the red particles. And each particle, all they're doing is they're just simply going left, right, left, right, left, right. But if you looked at the direction the wave energy is transferring, so this could be like a top view of like maybe like a water tank or something, if you want to think of it like that. If you put like an object on top of it, it almost seems like it's being carried along in this direction towards the right. I don't know if you can see the mouse cursor. I'm assuming you can, but it does seem like the energy is going towards the right. Okay, so let's go back here now and just summarize this. So what's a particle doing? Well, using the example I had a particle that was going left and right, left and right, left and right. And then what direction was the wave energy transferring? The wave energy was transferring towards the right. So these guys are actually perfectly in line with each other. When the particle is vibrating in a certain direction, there would be a 0-degree angle between the two, and then when it's going in an opposite direction, 180. But nonetheless, they are directly in line. Now we're going to have to look at a longitudinal wave a little bit differently. So in a longitudinal wave, what you're going to see is there's going to be regions where the particles are very dense and regions where the particles are a bit more separated. So again, let's go back to the animation again. Okay, so if I look at this longitudinal wave, okay, I'm following the mouse cursor here. As I follow this mouse cursor, it seems like this area, this vertical line of the mouse cursor, has a region where the particles are a bit more densely packed. And then halfway in between one of those, it looks like this is an area where the particles are a little bit less dense, okay? So I hope you can see that. There's like an area where it seems like there's like a very dense, the particles are densely packed together, and then in between them, they're a little bit more spaced out. The example I'm going to use is of a spring. And to show the spring here, An area of compression would be an area where your medium is the most dense. Well, so in this case, your medium would be the particles that make the spring up. And if you look at this area, well, the spring's a bit more compressed together. So there's more particles in this volume that I've highlighted here. So if the particle density is larger, we call that an area of compression. An area of rarefaction. The way I memorize this is I think of like rarely and rarefaction. So rarely as in terms of there's not very many particles there. Rarefaction would be an area where the medium is least dense. So if we looked at the illustration here, this could be like a region where the spring is a bit more stretched apart. Okay, so in this manner. Now, in terms of, we don't really define amplitude in terms of a longitudinal wave, because like you can't really see like a specific crest or a trough. But what we can do is we can define the wavelength. So there's a couple ways you could define it. You could say the wavelength is the region from the center of an area of one compression to the center of the area of the next compression. So this would be my wavelength. Or you could do, let's do it in purple here. You could go from like the center of an area of rarefaction to the center area of the next rarefaction. So a couple ways you can define that. Wave pulses. If you have a portion of a wave where the wave just has an upward portion, like kind of like a bump on the road, we refer to that as being a positive wave pulse. Okay, positive wave pulse would just have a positive amplitude to it. A negative wave pulse, on the other hand, would be an area where you have a bit of a dip in the road. And if you have a dip in the road, you'd actually have a negative amplitude because you're going down to a trough. As for a positive wave pulse, you'd be going up to a crest. The V here makes reference to the wave speed, but we'll talk about the wave speed in the next lesson. Okay, last thing, we're just going to talk about what it means for waves to be in phase or out of phase, or particles to be in phase or out of phase. Different waves are in phase when they vibrate nicely together. So this illustration shows 5 different waves, and again, they're just being illustrated at different colors. Waves that are perfectly in phase means you could like nicely stack them vertically on top of each other. And I could do that. If I took any of those waves and just moved them down or up, I could have it perfectly overlap one of the other ones. If we want to look at points at a wave that are in phase, points on a wave that are in phase are separated by, I said one wavelength, but it could actually be a whole number multiple of wavelengths. So if I look at the illustration here, point A and point B, again, a wavelength is the horizontal distance where the wave starts to repeat itself again. So points A and points B are a single wavelength apart, okay, lambda apart. C and D are also one wavelength apart. D and E are also one wavelength apart. So if points on a wave are separated by a one wavelength or a whole number multiple of a wavelength, so for example, C and E will be separated by 2 wavelengths, so this one plus this one, they're also in phase. Okay, so just a couple different ways to describe like what it means for a wave to be in phase or for particles in those waves to be in phase. Out of phase, on the other hand, the waves do not vibrate together. So you've got a bit of a jumbled mess here. If you could only move these waves vertically up or vertically down, you could not actually make any of them perfectly overlap. Okay, so if you can't stack them like really nicely, we'd say the waves are out of phase. In terms of what this means for points on a wave, well, if they're not separated by exactly a wavelength or whole number multiple of wavelength, then they are not in phase. So there's a bunch of examples here. So A would not be in phase with C, A would not be in phase with D. A would also not be in phase with E. Also, B would not be in phase with C. B would not be in phase with D. And B would not be in phase with E. Okay, so that's it for this lesson. And you can complete a hand-in assignment that's called Mechanical Waves. And I'll talk to you in the next lesson when we get into a bit more of a discussion on wave speed. And we'll talk about some other properties of a wave. No, I don't think we get into interference just quite yet, but we're definitely going to talk about what happens when waves strike specific types of boundaries. Okay, and I'll talk to you